Let's see why distinguishing between paired data and independent data is so important. Now, suppose we are trying to figure out, do people have bigger left feet or right feet on average? So we take everybody in the whole world, measure their left foot, measure their right foot, and see what average is bigger. Maybe it's the same. I mean, is it likely to be exactly the same to the million, billionth, trillionth decimal place? Probably not, but I bet you it's pretty close. However, let's say, for instance, that people, on average, have a 1/10 of an inch bigger left foot compared to their right foot. Now, we don't know that's the case. But let's just say if we were to do that for everybody in the whole entire world, measure their left foot and right foot, their left foot would be a 1/10 of an inch bigger. So to figure out which foot's bigger, again, we don't know this. Imagine we took a sample of 30 people and we measured their left foot and their right foot. What I did is I created a simulation where the average person's left foot is a 1/10 of an inch bigger than right foot. That's not to say everybody's left foot is a 1/10 of an inch bigger. Some people have more than a 0.1 inch difference. Some people have less than a 0.1 inch difference. And so with this simulation, I randomly sampled 30 people and I made a box plot of their left feet and their right feet. I bet if you were to look at these box plots, I don't think you'd be able to detect a difference. And that's because many times when you're dealing with paired data, there may be a difference between your two sets of data in terms of the average. But if that difference is very small in comparison to the spread of your data, then it's going to be very difficult to detect or see. In this case, we see observations that have about a 5-inch foot compared to a 14-inch foot. I mean, that's a span of 9 inches. And the difference between left feet and right foot is only 0.1 inch. So that difference is very small in comparison to the spread of your data. And if that's the case, it's very hard to detect differences in means when you have a small difference in your data sets compared to the spread of your data. However, when you deal with paired data, you can do something that can decrease the spread. What we can do is look at the difference between the pairs of observations. For instance, if we look at people's left feet versus their right feet, maybe person 1 had a left foot of size 12.5 and a right foot of size 12.3. Person 2 had a left foot of size 6.1 and a size 6.1. Person 3 had a left foot of size 8.7 and a right foot of size 8.8. What we're trying to test is there a difference between the mean of left feet versus the mean of right feet? So what we can do, since this is paired data, we can find the difference between each pair of individual observations. Let's find a new column of data which we'll call the differences. And we'll take left minus right. 12.5 minus 12.3 is 0.2. 6.1 minus 6.1 is 0. 8.7 minus 8.8, that's minus 0.1. We just found the difference between each pair of observations. And what we're going to do now is solely use this single column of data. That's the only data set we're going to use. We don't care about our previous two sets of data. We're only going to be analyzing the differences. And here's why this is so important. Is look at the spread of our new data set. Right, the spread of our new data set spans 0.3 inches. 0.2 to negative 0.1 to 0.3 inches. Our spread has shrunk drastically. Look at the spread of our other set of data. If we just look at the range of these things, 12.5 to 6.1, that's 6.4 inches. The reason paired data is so advantageous is because it reduces variability, it reduces spread. When we look at individual differences, it doesn't matter that some people had big feet or some people had small feet, right? That matters when we look at those variables independently, right? Some people have small feet, some people have big feet. We look at that spread. But what the difference is, we get rid of that variability, right? By looking at the differences, it doesn't matter if people have big feet or left feet. We're subtracting out the other size of their foot and getting rid of that extra variability. It's much easier to see differences between two sets of data if they're paired because it reduces the spread and reduces variability. It's essentially going to magnify that difference for us by reducing the spread. And something that's very important to note is that if we were to look at the mean of left feet minus the mean of right feet, that's essentially the sample statistic that we use to estimate our population parameter. What's really important to note is the difference between these two means equals what we call D bar, which is the sample mean of the differences. Those two values are exactly the same. So the center of your data set does not change. What does change is the spread, or rather, what can change is the spread. We have a new piece of information or new notation too called mu-d, which is down here. Mu-d. This represents the population mean of the differences. So I'll just write pop mean of differences. And now we can see here on this box plot that we're not comparing two sets of data anymore. We're looking at a singular column of data, the differences. So this column right here, this red column of data, is representing those differences. And now what we're interested in is if mu-d differs from 0. Because if we remember, when your difference between your population means equaled 0, right, or differs from 0, that represents a difference from means. Right? One of the means is bigger than another. Now, if mu-d is different from 0, because they equal the same exact value, we can use this singular set of data to see if one of our means is bigger than the other. And it's going to be easier when looking at paired data because it will reduce your spread, or can reduce your spread.